In the back of your spirals, we are trying to answer as much as we know about this function. We might actually answer a little bit more as we go. You guys are supposed to factor. That was a little confusing at first until maybe you heard or you thought to do what? Separate the top and the bottom, right? Then you would have hopefully gotten x plus 2 times x minus 2 all over x minus 2 and x minus 1. Stop. Did you factor it correctly?
Yes.
Nice. What could you do to keep going? Take out meaning reduce, right? Okay. And we can say x plus 2 over x minus 1 for x. Who did we take away that still technically is not allowed to? You have to state that so that still has as much meaning. I know, Lonnie. Okay. Coming back. I was talking to the video. Coming back. I realized she wasn't here. How do we do the y-intercept? Oh, for x. Whew. I'm almost got intense. So, y equals 0 minus 4. That's easy, right, guys? 0 minus 0 plus 2 equals negative 4 over 2, which is? Could we have plugged it in here also? Yeah. See how much easier maybe that would have been? It wasn't super hard right there, but we could have plugged it in here because remember, this is the exact same as that, but with a problem at 2. Don't make a problem at 2. Okay, x-intercept. Now what? Plug it in for y. I totally agree. Equals. I could set it equal to this whole thing, but we factored it. I could set it equal to this whole thing, but we simplified it. I'm going to set it equal to, and there's a very particular reason. How do I get a 0 out of a division? Does it come from the top or from the bottom? 0 in the bottom, isn't that undefined? How do I get to actually equal 0? Well, guys, how would you solve this? How did you solve this? Multiply by the denominator. I need to move that x minus 1 because he doesn't belong, and move that x minus 1 calm down. And I end up with, what's 0 times anybody?
0.
Now, did any of you guys start from the beginning and get plus or minus 2? Okay, never mind. If that's not a mistake, then we're good. If you did get plus or minus 2, you'd have to remind yourselves 2 isn't allowed. 2 isn't allowed. Okay, so we have our, I'm going to write it pretty. Okay, we have our factored form, we have our y-intercept, we have our x-intercept. Our next question was, are there any holes? Yes or no, and why?
Yeah.
Yes. Good. Where?
X equals 2.
Why?
Because it's x minus in the top and the bottom is canceled.
X minus 2 is the top and the bottom. It can reduce, it can factor, and cancel. Reduce is better, which means it's removable. And if you want to think about it, plug in 2, you get 0 over 0. That's a whole. Right? Vertical asymptote. Wait. Do we know more than this? Could we actually figure out exactly where he is?
Plug it in.
Plug in here? Uh-oh, that's 0 over 0.
Oh, yeah.
It can't equal 2, so I can't plug it in there. But where can I plug it in? Because when I cancel out the whole, I can see where he should be, but he's not. I can see where he should be, but he's not. So if I plug in 2, 2 plus 2 is 4 over 2 minus 1. I know where even the point is to put the whole. Which may be nice and may prove helpful as I go to sketch a graph. Vertical asymptotes. Yes or no? Yes. Where is there a vertical asymptote? At x equals not 2. 2 is the whole. We removed the hole. What domain problem remains and cannot be removed? You see it? Holes come from the part that factors and cancels, reduces away. Vertical asymptotes are the undefined points that remain.
So it's just the hole? The x equals 2?
Yeah, only a hole, because it was removed. That's the hole. And once he's gone, x equals 1 is the vertical asymptote. And we keep it like this because this one was a point, technically, right? This one is a whole vertical line, so it's that whole x equals 1. Horizontal asymptote days, what do we do? Powers. And we ask ourselves, who wins? Top, bottom, or tie? They're a tie. So since they're a tie, ties don't lie. We have a horizontal asymptote at y equals the ratio of the leading coefficients. 1 over 1 is dun, dun, dun. Almost done. What else do we have to do? No, you guys didn't need to sketch. We're going to go ahead and work together to sketch. You ready? Let's go ahead and take both of these pages. Let's see if we can put everything together. Well, I know there's something going on at 1. There's something going on at -2. I know there's something going on. We'll just say that sounds about right, yeah? Okay, we know there's a hole at 2. Oh, we need one more, yeah? Okay. We know there's a hole at 2, 4. Oh, that's exciting. What else do we know? There's a y-intercept at -2. I like these ones where we have points. There's an x-intercept at -2. There's a vertical asymptote at 1. Horizontal one at microphone back on. Okay. Let's see if it keeps working without the microphone on. Got my sound on. Some of you could probably guess what this looks like, yeah? What would you guess? Show me with your hands. Like a this thing? And like a this a thing? Ish? Okay, how do we know for sure? Oh, we need to look at like the end behavior stuff. Well, wait. We already know the end behavior. What's it getting closer and closer and closer to? Yeah, which if it comes from below, it's probably just going. Every now and then it might be a weird function that actually passes and then, but that's really weird.
And because they're reflected across the asymptotes, right?
Usually there's some sort of symmetry. So if you see this one, you're assuming that this one. That's true. How can we make, or I don't know, how can we know for sure? Because maybe it's something like this. And maybe it's something like this. And you might be like, that's not possible. It can't cross. It can't cross this one. Guess what, though? It's allowed to cross that one. Oh, that stink. How do we know for sure? Well, look. Can't I technically connect?
No.
No. And can't I technically connect?
No. What about the asymptotes?
I'm allowed to cross horizontal. I'm not allowed to cross vertical. Vertical is a domain problem that says no one's allowed. Horizontal just says, oh, what's going on down here?
That destroys everything I ever believed about horizontal asymptotes.
It's okay. Break you down to build you back up. Okay, so life lesson. this isn't the case?
Well, because it's just x.
Maybe a
plus
parent
n.
function.
The degree of the x.
That's kind of hard. The degree of the x? Maybe.
The last.
What's the difference between mine and yours? The behavior near the vertical asymptote. That was Jacob Gigante back in the day. So, coming back. I need to figure out what's going on by this vertical asymptote. If I can figure out what's going on here, I'll know whether you guys are right or whether I'm right. So what do? We say as. X. We spell as right. As. X. I just got too excited. Approaches. Who's that? 1. From. How do I show this? Yeah. 1 little negative, because it's from below, numbers a little bit less, remember? F of x is approaching, we'll come back. And as x approaches 1 positive, f of x is approaching. Now remember, it's a vertical asymptote. I know it's going to be an infinity. All I need to do is, do you remember this from yesterday? Yeah, plug it in. And what are we looking at? The number? The sign. I'm just checking the sign. So, what is a number a little bit less than 1?
9.
0 is a bit less than 9. 0.9 sounds great. 0.5 would be probably adequate. I'm taking my function, I'm taking my nice and pretty easy function and saying, hey, what happens if I plug in a 0.9 there and a 0.9 there? Positive on top, yep, 0.9, 0.99, 0.99, all of those are positive. Uh-oh, 0.9 minus 1, 0.99 minus 1, 0.99. Those are all. And a positive over a negative is a. So then what happens is I go to the next one and I plug in instead of a 0.9, maybe like a 1.1? Yes. 1.1, 1.1. On top, that's a positive. On bottom, 1.1 minus 1, 1.01 minus 1. All of those are. And a positive over a positive is a. Stink. So it was going down and it was going up. Guess who was right? No, you're right.
She let us win.
I'll let you win this time. You guys won. It was the easier solution.
I wonder what.
But
20,000
technically,
what?
just from the different clues, it could have been mine until we figured this out. Just from the clues. And I'm a calculus teacher, which means I've seen nasty functions that have looked like the other ones I showed you, right? Just letting you know. Just gotta be careful, gotta play it safe, gotta make sure we're doing things right. Life lesson to that too. So, going back. Did we review what we did yesterday? Horizontal asymptotes. Yes. Vertical asymptotes. Check. Behavior towards. What did we not write down yesterday? The one thing. Hey, look. We're done. What was the one thing we didn't get yesterday? Oh, this guy. This guy. Right here. In your notes. Doesn't this just talk through everything we just did? Decided to change things. Oh no! We'll go back one. Okay. Dun 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 dun. What did I leave out? I think I'm technically leaving holes out. Because technically this section doesn't talk about holes. Actually, it doesn't come in our book until a later section. But guys, if you talk about vertical asymptotes, how can you not talk about holes? If you factor them away, how can we not talk about who they actually are, poor little guys? So we're including them, so that we don't have to include them later. And this is whenever you're dealing with a function that has a top and a bottom, is a ratio to two functions. Whenever they're rational functions. Yeah, so what's going on for simplify? Factor. And, if possible, reduce, right? The very first step, try to factor. Try to reduce if possible. Try to simplify. When I say find, plot the y-intercept, what did you guys have to do? Set. Which one? For sure? Yeah. Set x equal to 0. For the x-intercept, set y equal to 0. How do you find the point of the whole?
If there's a part in the top and one in the bottom that reduces.
There's a hole when the original factors and reduces. Does that make sense? When the original you can factor and reduce a factor from the top and the bottom. And to find the actual point, plug into the reduced, I ran out of room, form. Plug into the reduced form. You reduce it, you have a nicer function now without the hole, but you still have to restrict the domain to say, you still need to state that x cannot equal that original discontinuity. And if you want to find the point of the hole, you plug into the reduced one, like we did in our example.
What if there's like something that would reduce? So you
No holes. Yeah, no holes. And by reducing, I don't just mean numbers, I mean whole factors, right? Fine, sketch, vertical asymptotes. How? He's the discontinuities, or he's the zeros in the denominator, or the factors in the denominator. That don't reduce. Vertical asymptotes, they're the ones that are still stuck. They're the ones that are still in the denominator. And I'm going to say, just to help you out, check behavior. Why? Because we know how to do that, and then we know for sure what's going on around that vertical asymptote, like the example that we saw in the back of our spiral.
The reduction in number 1, you also have to put a domain. Problem.
Factor and reduce, state the domain restriction. Yeah, we can put that as a reminder. Something that you could forget. If you reduce out a factor, you have to just state the domain restriction that it had, or else it just disappears and you never know. Horizontal asymptotes. I'm not going to say the entire thing because we have it in our notes, but how do we find them, or how do we approach a horizontal asymptote? Good. Check the degrees of the top and bottom. Yeah, so the powers of x in the top and the bottom, asking yourself the questions, who wins? Top wins, no HA. If we have a tie, or if the bottom wins, HAs we got them, right?
Yeah.
We have horizontal asymptotes. There's a tie, ratio of the coefficient. If the bottom wins, it's really pulling it down to 0. Now, number 7, we didn't actually need to do this one in our example because we checked the behavior around the vertical asymptote and we kind of just saw how the function was going. However, number 7 is available. Number 7 says, hey, what we can find, 1 through 6, it's good, but it doesn't necessarily get you a perfect graph every time. Kind of like that weird one I showed you that could have been a graph until we checked the behavior. So number 7 says, if you're not for sure, find and plot a few test points. Remember when we were doing our big degree polynomials in chapter 1? And we made a table after making our zeros, and we just picked a point from every single place and just said, hey, it gives us a few more points. We know better how the function's moving, changing, what the picture looks like. So number 7, if you need a little more information, just plug in a point here and there, kind of spread out throughout your picture. So in ours, we could have, in between each of our different characteristics, for instance, we could have plugged in a point like in between here to make sure he was going down. We could have plugged in a point in between here to make sure he was going up, etc. We could have plugged in maybe a couple points over here to make sure he was going down, etc. But I just said, if necessary, in your notes, right? Because we didn't really need it in this one. And then last but not least, use smooth curves to connect, complete. The only time you'll have like sharp turns would be like maybe something with an absolute value or some other funny functions that you're not going to see right now. That you're not going to see right now. With this, oh my goodness, I think we're done. So get out that homework 2.6. Wait, did we finish it?
Yeah, we just didn't sketch.
We just didn't do the sketch. So let's go ahead and check up until the sketching stuff. Sound good? It's going to be taped. If you weren't able to totally finish, you can see it quickly tonight. As you guys wait for me to pull it up because I didn't have it totally ready, you're getting your spirals out to check. But let's go ahead and also have you write down to make sure we get into 2.7 because we have to get into 2.7 today. Let me go ahead and have you write down the first page of 2.7. So get your homework ready, get your colored pen out, write down the first page of 2.7. And then we'll be good to go in just a second. And if you guys look, this is the final section of chapter 2. What are we seeing in section 2.7? Look at the title.
Nonlinear inequalities.
Inequalities, but ones that are worse than lines. So like inequalities with quadratics in them. That sort of thing. Number 2, vertical asymptote. Number 8, they actually had you plugging into a table, so you were allowed to use your graphing calculator, but you were coming from below 2 and coming from above 2. And they were trying to have you notice from below 2, hey, it's going to negative infinity, and from above 2, it's going to positive infinity. But guys, isn't our trick easier than making a whole huge table and having to plug in lots of points? That's what I thought, right? So we're leaving the table behind. We can go better than that. That was towards negative 2, and then towards positive 2. As you come from above, it's going to go to positive infinity, or increase without bound. And as you come from below, it's going to go to negative infinity, or decrease without bound. What do you think I like better? F of x decreasing without bound, or f of x approaching negative infinity? Oh, yeah. Use the shortcut thing. Don't just steal their words. You guys can write it better and quicker, faster, simpler, etc. Make sense? So the book gets the idea across, but ours is better, and it prepares us for what's to come. Moving on. Number 12. Domain. Everything but negative 3/2 from the denominator. Vertical asymptote is at negative 3/2 from the denominator. Horizontal asymptote, it's a little weird. It's a little weird. You could have just taken it the way it was. You didn't have to rewrite it. They just rewrote it so that the leading coefficients were in the beginning. But you could have just looked at it and said, hey, look, there's a negative 7 next to that x, and there's a positive 2 next to that x. Negative 7/2 is the horizontal asymptote because the degrees are tied. Does that answer your question?
I was just confused on how you got the negative 3 over 2.
Oh, look at that denominator. Set him equal to 0, right? minus the
Oh,
3
that's right.
divided 2. Only, now guys, hold on. This is something calculus kids mess up on. Where are the domain restrictions? Where are the vertical asymptotes? In the top or in the bottom? Just the denominator. Just the bottom. I'm not kidding. A lot of them missed it on one of their first tests. Okay. Number 22. Once again, they rewrote it to make it look pretty, but technically this version is fine. What they did is they pulled out a -1 top and bottom and made it look different by switching all the signs, but this version is fine. Domain, all real numbers but 1. X-intercept. Oh, hey, wait, isn't this what we were just doing today? Okay, so maybe some of you guys didn't get to 22. We're just peeking at it really fast. We're peeking at it really fast, but technically it's going to be on the video, so if you do get to finish it tonight and want to go check it quick, come tomorrow if you had any questions on what did or didn't work out. Cool? Cool, cool, cool? Okay. Now, they did a cool little table, blah, blah, blah. Do you think we would have needed the table? Probably not. I bet we could have gotten that. Looked a lot like our example in the beginning of class. But you did get your x-intercept, y-intercept, vertical asymptote, horizontal asymptote. They didn't say hole. I know, they haven't taught it yet, right? But we're cool, and we already know where holes are, but there aren't any. And we're done. 42, oh, 40, I don't even know. 42, 43, 44. I tried to put them all together. E, A, F. It's like ear, but with an F. Anyway. And I put 43 because I was too lazy to take 2 pictures of 42. What was F?
I only had A, B, C, and D.
There was no F?
Yeah.
Sometimes the book, remember, it's the new one that
No,
was...
I didn't get the book and got all mine.
Oh. But it might be cut off in the book. Every now and then, like, the margins mess things up. This is 2-5. 2-6. Number 44? Yeah, there was no F. Hold on. So 42, wait, give me a second. 42 does go with A. Oh, not E. Scratch that. 42 goes with A. 42 goes with A. 43 goes with C. And 44 goes with B. A, C, B. A, C, B. Right? There you go. Let's make them bold just so that they, I don't know, stick out. Okay, number 60. Uh-oh. Doesn't that look kind of like the other one we just did? Struggle. Who did he have? Oh no, we didn't review this today, guys. What's a slant asymptote? And when does it happen? Oops. We didn't review this today. We did it quick yesterday. A slant asymptote. When the top is greater by 1, how do we find it? Divide. And we take everything out of the answer but the remainder and set y equal to, graph that line, and that function is going to get closer, 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 closer to it, like in the example that you can see right here. Uh-oh. Closer, 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 closer. But some of you need to keep on looking at number 60 tonight. Okay? So we'll come back to that tomorrow. You can pause this in the video. You can double check your answers later on. Some of you might have them right now. Do you have to do the table? Only if you need more points. Only if you need more points and you can't make it work without. And then last but not least, number 80. True, true, false. True, true, false. Luca.
I put a B is false because the horizontal asymptote is not at y equals 0.
True, but the horizontal asymptote can be at a number. I'm thinking that's what's going on with the true false, but I don't have it memorized. Give me 1 second. Number B, letter B.
Yeah, it would be. I put it's false because horizontal asymptote is not at y equals 0.
Oh, but remember, the horizontal asymptote is only 0 when the bottom wins. So because it's at a number, they have to be equal because it's a ratio. Does that make sense? All right, cool kids. We'll go over questions on this tomorrow. So for right now, you saw the answers. You can watch the video tonight and double check the answers once you finish. If you haven't finished, But for right now, we are going to start section 2.7 and get as far as we can. If you look on the backboard, technically, I have 2.7 homework due on Friday. So do as much as you can by tomorrow. My poor little people going on the retreat. Or do a little bit of homework on Saturday. Yay! Before you leave. Okay, so. Or Tuesday when you get back. Yay! Stay up all night and talk to parents and friends and whatnot about the retreat. Or crash and die after the retreat. So. You guys already wrote this, right?
Yeah.
Let's go. Non-linear inequalities. Guess what? You have all the fundamentals of doing this section right now. You just need to see them all put into play. All applied. The name of the game in section 2.7 is a sign chart. What? A sign chart? Weren't those things that we made back in the day when we were trying to graph a polynomial and we'd make a number line and we would put like certain special points? And then we would pick like some other in-between points and we would test stuff in a table? Some of you are like, I have no idea what you're doing. Anyway, this was the sign chart. We would put in some zeros, like -2 and 0. And then we would pick, hey, what's something on this side? -3 sounds good to me. How about -1? Yep. And how about 1? And we would go plug it and chug in. That's all we need for section 2.7. Done. Let's talk about it though. Let's talk about it though. A polynomial can only change at its zeros. Does that make sense? Polynomial is continuous. It has to continuously go through values, so it can only go from positive to negative if it goes through a 0. Or it can only go from negative to positive if it goes through a 0. Anyone remember what theorem guarantees this? Go from negative to positive or positive to negative, you have to go in between.
Oh, it's the what? This cartridge
I was
rule.
2 feet, and now I'm 6 feet. I had to be everything in between feet. You know what I'm saying?
What's the first letter? Yeah.
I just gave it to you.
What sign language though?
Go on second. No one knows? Hang on. I.
Intermediate value theorem.
There it is.
That's what I was thinking.
Intermediate value. Intermediate value theorem. Intermediate value theorem. Anyway, long story short. If a polynomial can only change signs at its zeros, and if an inequality is all about signs, whether above or below, then we need to start by finding key numbers for polynomials, which are just the zeros. Set equal to 0, and we have the key numbers. We just have a new name for them. So, steps to solving. Literally, we're here? Yes, we're here. Let's go. Steps to solving. What? Inequalities. Nasty ones. Steps to solving. Inequalities, but nasty ones. Nasty ones where there are lots of factors involved. Steps to solving. Find all the key numbers. Mark them in a sign chart. Plug a test value from each interval into the polynomial and say, does it work or does it not? I know, right? Compare the signs to the original inequality. Kiddos, listen, some of you really need to get ahead, right? I'm going to do an example right now. As classes are changing, you can check on it tonight if you want to get ahead. Get out of here, I'll see you tomorrow. Toodles. I'm going to randomly be talking to myself, not really, but see you later on tonight. Key numbers.
We should check if they'll Scarlet really quick.
No?
So funny.
The phone is Chuck, is that a drop trap? What a bomb.
So our key numbers are found by factoring, and then setting each factor equal to 0. We take those key numbers and we mark them in a number line. We have our negative 2, and we have our 3. Our next goal is to test. Our next goal is to test, but the nice thing is we only need to test numbers in each of the intervals, like what's something to the left of -2? I don't know, how about -3? What's something in between -2 and 3? How about 0? And what's something on the right of 3? How about 4? Now at this point, all we have to do is plug into our function. Wait, who's our function? Our function is basically our entire inequality statement. So it's a little bit different than before, but we're plugging into our inequality. And we're basically asking ourselves the question, true or false? So when we plug in -3, I'm going to do it kind of quickly, but let me show you what I'm doing. When we plug in -3, we get -3 plus 3 times -3 plus 2 greater than 0, which ends up being, oh, -3, I messed that up, huh? -3. -6 times -1 greater than 0, 6 greater than 0, and the question is true or false? True. Or if you want, you could technically put this little statement in and say, hey, that's true. Then I'm going to go ahead and plug in 0. For x equals 0, if I plug in 0 minus 3, remember I'm plugging into my original inequality up here and asking myself true or false. 0 minus 3 times 0 plus 2 greater than 0. I end up with -3 times 2 greater than 0, -6 greater than 0. Is that true? A definitive? No. So that one is false. Okay, we can go one more interval. We can go to x equals 4, plug in chug. 4 minus 3 times 4 plus 2 greater than 0. 1 times 6 greater than 0. 6 greater than 0. Is that true? Ooh, yeah. Mark it true. And then we have to put all of our information together. We have to take our little sign chart that we made and say, all right, fine. What are the solutions to this entire problem? I'm going to just move my work down really quickly, just so I have some space. But at the end of the day, for what intervals did I get true statements in my inequality? My solutions will be x is within -infinity to -3. At -3 was a 0. And since my inequality is just a less than and not a less than or equal to, we cannot include -3. Because I cannot include my zeros. But I also have another part to my solution. I also have from 4 to infinity, but I do not put the middle part because the middle part was false. Dun, 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 dun. That's basically 2-7 in a nutshell. We'll see harder problems tomorrow. Bye, guys.